Hi, welcome everybody back to our IPAC seminar this year. This is our second series, and there will be 3 lectures given by all the 3 authors of this paper called Alpha Chromatic Symmetric Functions. Today, the first speaker will be Misu Yu. It is actually our honor to have all 3 of them to give the talks, especially one of our main organizer, which is Jim Halligan, is going to give the talk next week. So stay tuned. Anyway, so I will give the time to Misu. All right, go ahead.
Thank you very much. I want to thank the organizers for giving me a chance to speak here. In the recently published paper, Jim, Jaesung, and I introduced this symmetric function family called alpha chromatic symmetric functions. And we proved several combinatorial identities. And we're going to show the results through these 3 lectures, and this is the first one. So I'm going to define the alpha chromatic symmetric functions, and then I'll explain how we got to work on this problem and the combinatorial results you will see in the second and third lectures. So let me start by making observation that there are 2 families of symmetric functions indexed by Dick path. So one is the chromatic symmetric functions, and the other is the unicellular LLT polynomials. So the chromatic quasi-symmetric functions are defined over proper colorings. The coloring is an integer value assigning function on the vertices of the graph. And the coloring being proper means that if 2 vertices are connected by an edge, then the coloring values of those vertices should be different. So these chromatic symmetric functions are defined over the simple graphs, but if the graph is the incomparability graph of the natural unit interval order, in that case, this graph can be included in the picture of the Dick path. So I'm just defining the chromatic symmetric functions over the Dick path. And so the proper condition for the chromatic functions defined over the Dick path is such that for those cells between the diagonal and the Dick path, for this, for example, the value on this column and the value in this row should be different. So that's what the proper coloring means. And then for the unicellular LLT polynomials, we consider all the words of length n with no conditions. And then for both polynomials, we're going to use the inv statistic for the Q statistic. So the inv statistic counts the number of cells between the Dick path and the main diagonal, such that you compare the value, for example, for here, you compare the value in this row and then this column. And whenever you have a larger number in the row than the value in the column, you count that as an inversion statistic. So for example, in this example, you compare for the cells between the Dick path and the diagonal, the values in the row and the column. And for example, here, 4 is larger than 3, so you put Q there. Of course, 5 is larger than 4, so here there is an inversion as well. And then 3 is larger than 2, so it gives Q. And 3 is larger than 1, so again, you have Q here, Q here. And then 2 is larger than 1, so you have Q here. So from this coloring, you read out Q to the 6 because there are 6 inversion pairs. And then the coloring value on here, you will give the monomial for this coloring. So you have 3 ones, means you have x1 cubed, and then x2 squared, x3 squared, x4 squared, and x5. So for the chromatic symmetric functions, you consider all the possible proper colorings and sum those up, and that will give the chromatic symmetric functions. And for the unicellular LLT polynomials, you drop the proper condition and do the same thing and add these up, and then you get the unicellular LT polynomials. But if you compare these definitions, they look very similar, except this small discrepancy that the chromatic symmetric functions need this proper condition. Proper parking functions. So I'm not talking about the proper parking functions at the moment. Oh, proper coloring. So the coloring being proper means that if two vertices are connected by an edge, then you color those vertices with different colors. But in this picture, the vertices connected by an edge are for those for the cells between this thick path and the main diagonal. Then these are coloring values. So if there is an intersection between this column and row, between the thick path and the main diagonal, then you put different numbers in these cells. But for example, here, these values could be the same because this is not an edge in the incomparability graph. So that's what I mean by the proper coloring. Okay. So these two definitions look very similar, except this proper condition. And so there should be some relation between these two polynomials, and Carson and Mallet came up with the precise relationship in 2018 upon the proof of the shuffle conjecture. Namely, they are related to this via this plot-distic substitution. So this plot-distic substitution is a way of composing two symmetric functions. But in here, what it really does is just extending the set of variables by giving Q weight in one set of variables and giving some signs for the other set of variables. So we can simply understand this as extending the set of variables. And this is the starting point of the definition of our alpha chromatic symmetric functions. Let me copy this to define our chromatic symmetric alpha chromatic symmetric functions. So we have the Carson-Mallet relation over here, and to define our alpha chromatic symmetric functions, what I'm going to do is I'm going to replace this Q here within the plot-distic substitution by T, and then I'll let T equals Q to the alpha. So I'll just use this notation to denote the alpha chromatic symmetric function indexed by the dict-path pi. And I said I'm going to put Q to the alpha here, and then divide by Q minus 1 to the n. But in terms of the original chromatic symmetric function, what you're doing is here this square bracket is actually the plot-distic substitution. So in terms of the original chromatic symmetric function, what you're doing is you're multiplying this vector to your set of variables. And if alpha is a natural number, then what this vector is just a summation of Q to the 0 through Q to the alpha minus 1. So what this vector means, it's actually you're extending the set of variables to the ones with the Q weights. So you have the X variables, and then with Q weight, and then Q squared, and so on up to Q to the alpha minus 1. So it's like you're using two different sets of colorings for the alpha chromatic symmetric functions. And this alpha, the Q weights will give the second coloring for the alpha chromatic symmetric functions. So this is the definition. Let me just compute a small example. When your dict path is 2, 3, 3, and then for the simplicity, I'll just let q equals 1 and write down the computation to see how the polynomials look. So here, M3 coefficient looks like this. And then M21 coefficient looks like this. And then this. So we can see that the monomial coefficients are not even alpha positive. So they are not in general monomial positive. But then what we observed is that if we use for example, alpha binomial coefficient, then they become positive. So for example, so here, since I'm using q equals 1, I can just use the binomial coefficient like this. So M3 coefficient looks like this. So in terms of this alpha plus k choose n basis, they become positive. Let me write down everything. In terms of this alpha plus k choose n basis, they become monomial positive. And it's the same for other binomial coefficient expansion. Namely, if we use alpha, so this is the following factorial, alpha minus 1, alpha minus 2. And then alpha 3.
Ms. Sue, there's a question in the chat.
Oh, I'm sorry. Oh, 2, 3, 3. So this is 3 by 3 board. And 2, 3, 3 looks like this. So basically, for the chromatic symmetric functions, you just fill these cells with proper coloring. But then for alpha chromatic symmetric functions, we're going to have another set of colorings. Alpha choose 3. Oh, this is 5. I'm sorry. I'm sorry. I just want to write it quick. So this is M21. And then 6. I just want to show you the positivity in terms of these binomial coefficients. So here are some observations. Each coefficient is a polynomial in alpha of degree n, and the constant term is 0. And the coefficients are in the span of these alpha polynomials. And what we're going to show, you are going to see in the next 2 lectures is that the alpha chromatic symmetric functions are positive in these expansions in shear functions as well as monomial symmetric functions. But I'm not going to show those results, but what I'm going to show is how we get to define those alpha chromatic symmetric functions and where the problem starts. So let me begin with reminding you the McDonald polynomials. So in 1988, McDonald came up with this family of symmetric functions with two parameters, Q and T, characterized by two properties. One is the triangularity in terms of the monomial symmetric functions, and the other is orthogonality with respect to the QT analog of the Hall inner product. They are important in a sense that they generalize all the known symmetric function bases, namely when Q equals T, they become the Schur functions. And when T equals 1, they become the monomial symmetric functions. When Q equals 1, they become the elementary symmetric function indexed by the transposed partition shape. And when the indexing partition shape is one column shape, then the McDonald polynomials just become the elementary symmetric function. But we know that that is just a Schur function indexed by one column shape. And when Q equals 0, they become the Hall-Littlewood polynomials with one parameter T. So in a sense that they generalize all the non-symmetric functions, it's important. And upon the introduction, McDonald also defined the integral form McDonald polynomials. So if you consider the McDonald polynomials in terms of the monomials, the coefficients are not polynomials, but they are rational functions. And the integral form is defined such that the monomial coefficients become Qt positive. So to do that, what we need to do is we need to multiply this vector Q to the arm times T to the leg plus 1 over all the cells in the partition shape mu to the original McDonald polynomials, where, say, mu is like this, and then your cell C is here, then the number of cells to the right of C is the arm length of C, and then the number of cells above C is the leg length of C. So here this is arm and this is leg, and you compute all those factors over all the cells within mu and multiply that to the original McDonald. Then that will get rid of the denominators in the monomial expansion, and that will define the integral for McDonald's. And what McDonald observed is that if you define the integral form in this way and expand that in terms of the modified Schur functions, the modified Schur function means rather than just thinking of x, you think about let this substitute x here. So in your x variable, you also consider x as well, and then with the t weight variables with some sign. And so this is modified Schur function. And in terms of this modified Schur function, the integral form has this expansion. And McDonald conjectured that these coefficients are Qt positive, and this is the famous McDonald's positivity conjecture. And of course, we know that in 2002, Mark Heyman proved that they are positive. So this is a theorem. But the combinatorial description for these Qt Casca polynomials are not known, and this is a huge problem in algebraic combinatorics. But everybody was busy of considering the combinatorics of this polynomial, but Jim Hageland changed his perspective and he considered the Schur expansion of this integral form itself and conjectured that if you replace t in the integral form McDonald by q to the alpha, and divide that by 1 minus q to the n, then it has a positive Schur coefficient. And that was his conjecture, Jim's conjecture. In fact, we conjecture very explicit form of Schur expansion of the integral form McDonald. Namely, it's going to be sum over all the semi-standard Young tableau of shape lambda prime at weight mu prime. And then you're going to multiply over all the cells of mu, 1 minus t to the leg plus 1, and then q to the. This is something that we don't know, which depends on all the C and the semi-standard Young tableau T. And then q to the charge statistic of T. And there will be the Schur coefficient. So we expect that the Schur coefficient is in this form, but then we don't know what this Q statistic is exactly. But we figured out in some forms of mu, like when mu is a hook shape or two-row shape or two-column shape, we figured out how these Q statistics are. But in other cases, we don't know. So this is a conjecture. But then oh, this is charge statistic. It's already known by Lascaux and Schuchenberger. I'm not going to explain how you compute this charge statistic, but that's so I mentioned about the Hall-Littlewood expansion polynomials, and this charge statistic gives the Q statistic for the Casca-Forks polynomial, which gives the Schur coefficients of modified Hall-Littlewood polynomials. But the description for the charge statistic is quite complicated, so I'm not going to go over the details. But let's pause here and think about the relationship between so I haven't talked about it yet. So the from this definition that the integral form has Qt positive coefficient in terms of this modified Schur functions, so we can just define the modified McDonald polynomials h mu by the integral form platistically substitute x divide by 1 minus t. Then by definition, the Schur coefficient of this modified McDonald becomes this Qt positive polynomial. And then we can observe that this relation here, I mean the definition of the modified McDonald, is by dividing x by 1 minus t and platistically substitute. And we have seen this relationship before in the Carson-Melley relation. So let me make an analogy. So here I just defined this modified McDonald by using this integral form McDonald via this platistic substitution, x over 1 minus t. And then the unicellular LRT polynomials and the chromatic symmetric functions also had this kind of similar relationship. So we can make a parallel analogy of these two relationships. And we observe that the Schur positivity on the functions on the right-hand side correspond to the E positivity of the functions on the left-hand side. So these functions have Schur positivity. And the chromatic symmetric functions, I mean, the E positivity of the chromatic symmetric functions is huge conjecture. And when Q equals 1, it's proved recently, but when Q is arbitrary, it's still a conjecture. And what So what Jason conjectured is that also the integral form has certain kind of e-positivity in that sense. So let me explain about that a little bit more. Before we go to that direction, let me mention about the Hageland-Wilson conjecture. Hageland and Wilson also considered this form, the integral form, and here they replaced t by q to the minus alpha, and then divide that by q minus 1 to the n. And if you consider the Schur coefficients of that form, then after taking care of certain q negative power, the Schur coefficients become positive q polynomials, and that was the Hageland-Wilson conjecture. And Jason's conjecture was about this e-positivity of the integral form that I mentioned before. So it's going to be, so you have to take care of some q powers. We know what exactly that power is. And then j mu q to the minus alpha and divide by q minus 1 to the n. Then this is going to be E positive is the Jason's conjecture. And we proved that this E positivity is true when mu is a hook shape. So, and we have a combinatorial formula for the E expansion when mu is a hook shape. So that's what I'm going to show you now. So when mu is a hook shape, say the hook shape is this form. So the hook shape is like this. We have R many cells in the first row, and then S many cells in the first column above the first row. Then the E lambda coefficient of this integral form, where T is replaced by T inverse, is summation of certain vectors. And this is the Q negative power that I mentioned before. And then this weight comes from all the possible rearrangements of the parts of the lambda. Here, this is lambda. And then the weight is computed over all the rearrangements of the lambda, which is alpha here. And we were going to give the weights over all the cells in this shape, which is a transpose shape of the hook shape. So here are the descriptions, but I'm going to show you how you compute these coefficients in an example. So let me go over this example and show you how you compute this E coefficient. Say your hook shape is 5, 1, and then you want to compute E3 to 1 coefficient. And what you do is you consider all the possible rearrangements of 3 to 1, but what you need to do, I mean, you don't consider all the possible ones, but you only consider the ones which keep these two cells connected. Also, this is 5-1 transpose, and you consider all the possible rearrangements of 3 to 1, but those which keep these two cells connected. So for example, 3 to 1 is not the one that we consider because 3 to 1, it's breaking here. So we want these two cells connected together. So 3 to 1 is not a possible arrangement in here, but then 2 or 3 should come to the last. And there are 4 of them. So for example, say I consider 3, 1, 2. That means I divide the cells 3, 1, and 2. And then I mark the leading cells of the composition. And I'm going to give the weight. So for example, this is the common factor. And for each cell here, I'm going to give the weight. But for the leading cells, the weight is going to be t to the the length of the part. So this is 3. So this t to the 3 minus q to the leg of the cell. So the weight of the leading cell here is going to be t cubed minus 1 because there is no cell above this cell. And then the next two cells are not the leading cells of the composition. In that case, the weight is going to be, so let me write it down over here. The weight is t to the alpha minus q to the leg. If the C is the first cell of the composition, and t to the arm prime, and then q to the leg minus 1 otherwise. So arm prime is co-arm. So in the description of arm, we counted the cells to the right. This is arm. And co-arm is the number of cells to the left of C. This is A prime over here. So this is the weight of this leading cell here. And the second, third are not leading cells. We're going to use this weight in that case. But arm prime is 0, so you have q minus 1 and q squared minus 1 for the second and third cells. And then this is the leading cell of the size 1 part. So it's going to be t minus q cubed because the leg is 3. And then for this cell, it's t squared because the size of this part is 2 minus q to the 4 because the leg is 4. And then for the last cell, it's not the leading cell, so we're going to use this weight. And it's t, because for this one, this is the co-arm. And so this is t minus 1. So this will give one factor. And there are 3 others. So there is 1, 3, 2. This again keeps these two cells connected together. And then this is leading cell, this is leading cell, this is leading cell. So for those leading cells, we're going to use this weight. And for others, we're going to use this weight. And let me just write everything down very fast. So it's t minus 1 for the leading term. And then the second leading term, it's t cubed minus q. And then the second and third of the second part, you have q squared minus 1, q cubed minus 1, and then t squared minus q to the 4, and then t minus 1 again. So that this weight is for this shape. And let me just give the picture and weight quickly. So there are 2 more that we can consider. And the weight is now the 2, 1, 3 is one possible composition, and 1, 2, 3 is another possible composition. 2, 1, 3, and 1, 2, 3. And these are the leading cells. And then let me just write down the weights of the cells quickly. So the weight of this cell here is t squared minus 1. This is q minus 1. This is t minus q squared. This is t cubed minus q cubed. This is q to the minus q to the 4 minus 1. This is t minus 1. And for this one, it is t minus 1, t minus 1, t squared minus q, q squared minus 1, t cubed minus q cubed, q to the 4 minus 1, and t minus 1. So there are two more factors. There are two more factors added here, and they are, so you put here and here, and they will give the summation of these will give the E321 coefficient of the integral form McDonald indexed by 5,1 hook shape. And we can see that if you replace t by q to the alpha, everything is q to the something minus 1 form. So if you divide these things by q minus 1 to the n, then everything will be q integer. So you get the positivity. So as far as the hook shape goes, we know the E positivity of the Jesang's conjecture, but we're trying to see the coefficients in general. So there are such E positivity conjectures. And then let me also mention about the Jack polynomials. Now, if you replace q by t to the alpha in the integral form McDonald's, and then that divide by 1 minus t to the n, and if you let t goes to 1, then that's the definition of the Jack polynomials. Let me note that if we let, say, mu Twitter as so this is the form that occurred in Hageland conjecture. So this form was the thing that was conjectured to be sure positive. But if you take q goes to 1 limit in that form, and if you let Jamie Twitter as this limit, then Jamie Twitter and the Jack polynomials are related like this. So the form of integral form that we consider in Hageland's conjecture and Jack polynomials are related in certain sense. The reason why I mentioned this is because Nab and Tsai came up with the monomial positivity of the Jack polynomials. So there are combinatorial formula for the monomial expansions, and they are defined over, this is non-attacking filling. So the non-attacking filling means you fill the cells with numbers so that if your cell C is here, then you don't put the same numbers to the right of C, and then below of C to the left in the below row. So that's what this non-attacking filling means. And over those fillings, you compute these factors over all the cells of mu, such that the filling value of C is equal to the filling value below cell C. So you compute those factors, multiply those factors and add them up, then they will give the monomial coefficient. So you can see that they have the alpha positivity in the monomial expansion, but let me note that they are not sure positive. The sure coefficients are not positive. But what Alex Anderson, Hageland, and Wang observed in 2018 was that even though they are not sure positive, if you consider the alpha binomial coefficients of these Jack polynomials, then the coefficients are positive. They are conjecture, so it's not proved yet, but they observe this positivity in terms of this binomial coefficients. And I'm saying that this is the reason why we considered the alpha binomial expansions of our alpha chromatic symmetric functions. So what you are going to see in the next two lectures is that, so this was the definition of our alpha chromatic symmetric functions. So you're going to see in next two lectures is that we're going to apply the superiorization technique and the XY technique to this platistic substitution to see the monomial positivity in terms of the alpha binomial coefficients, and also the sure positivity in terms of these two kinds of alpha binomial coefficients. The sure positivity and monomial positivity in terms of two kinds of binomial coefficients, alpha plus k choose n basis and alpha choose k basis. And along the way, you're going to also see some relations to the root theory. And those are the things that you're going to see in the next two lectures. But for the rest of my time, I'm going to show some other properties. So we obtained the P expansion of this alpha chromatic symmetric functions, which is quite easy because of the definition. I mean, the nature of the definition that we use the platistic substitution. So that can be easily obtained from the P expansion of the original chromatic symmetric functions. So say we have this P expansion of the original chromatic symmetric functions, then our alpha chromatic symmetric functions, we defined that as platistic substitution of q to the alpha minus 1x over q minus 1. And then what you do is you just replace this x by this platism here. So you do the same thing, and this platism only affects the x variable, not the coefficients part. So they just stay there. And then you just replace x in p function by this. And then everything else stays the same. But then the property of the platism in the power sum is easy to compute. You just put everything out. So these are going to be q to the alpha times lambda I minus 1 over q to the lambda I minus 1 times p lambda of x. And then you can make this as the q integers. This is going to be alpha lambda I q integer. And then lambda I q. But then you have this, which was already there. So you have the same factors in here, and they will cancel. So this will be cancelled. So we only have this factory here. So by making by making this lattice substitution in the P expansion, you just add this alpha times lambda I factor more in the P expansion. That's just easy. So that's the P expansion of the alpha chromatic symmetric functions. And then let me mention about the symmetry of the coefficients. So if the Schur expansion of the alpha chromatic symmetric functions were this way in terms of the alpha plus k choose n basis, then if you make the transpose of lambda, so for example, if you consider as lambda prime coefficients, then in terms of the original coefficients, they are in this relationship. So you replace q by q inverse and multiply this factor, then you get the coefficient indexed by s lambda prime partition. So this also can be easily proved by using the known fact by Blasiak and et al. So let me refer Blasiak et al. Proved that they proved the general symmetry of the LLT polynomials, not only the unicellular LLT polynomials. So omega of LLT equals, so in this case, this LLT is unicellular LLT indexed by the dict-path pi, but their result is about general LLT polynomials, and this symmetry they have is more complicated. But if we only consider the unicellular LLT polynomials, then if you apply this omega involution to this unicellular LLT polynomials, then the result becomes like this. So we use this symmetry relation to our definition of the alpha chromatic symmetric functions, because we have LLT of platism q to the alpha minus 1x. So if you consider omega of LLT q to the alpha minus 1x, then because of this relation, you have q to the area and LLT, and then q inverse. Of course, you can also think this as q to the minus 1, and then minus alpha, because I want to make everything as q to the minus 1, like this. And then we use the Carson-Mellitt relation. Taking the omega involution to our alpha chromatic symmetric function is, because of this, divide by This also I did because I want to make this one as q to the -1. But then this is this can be simplified to like this. And then this symmetry. So here we already have this this function here. So you can basically put Q inverse in here, and then so this will be Q inverse. And what we need is the relationship between this binomial coefficient with minus alpha here, but we have the identity dealing with this Q binomial coefficient, replace this by minus alpha plus K. And then this relationship follows from the that relationship. So I'm not writing the details, but that's so let me write it down over here. If we use the minus alpha plus K choose N, Q binomial coefficient is equal to -1 to the N, Q to the N plus 1 choose 2 times alpha plus N -1 minus K choose N, Q binomial. So if we use this relationship in here, given this pure coefficient, then you can get this relationship right away. So that will give the symmetry relation. And that was what I wanted to talk today. And for the combinatorial positivities, you'll see in the next 2 lectures. Thanks a lot for listening.
Thank you so much, Mr. Les. Thanks the speaker. Very nice talk.
Mhm.
Any questions for me, Sue? So I do have one. I wanted like, so for the alpha, when you put alpha into like different numbers, including sometimes maybe rational numbers, is there something interesting combinatorially that you can talk about?
So as far as we observed, all the interesting combinatorics occurs when alpha is positive integer. For example, like the relation to the log theories and the sure positivity results. So I think we only considered the positive integer alpha values, and other than that, we haven't. I think we haven't experienced or experiments for other alpha values.
There is the negative alpha though for the J mu.
Oh, that's right. Yes. Yeah. When alpha is negative, then we observe this E positivity.
Mm-hmm.
Yeah.
I see. Thank you. All right. If no other questions, let's friends meet you again.
Thank you very much.
Thank you. So we will resume next week. So next week will be Jim and also Jason will be talking about different parts of the paper. Thank you so much for joining. And we will see each other next week. Bye. Have a nice weekend.